In this video, I would like to discuss a method. It's called tabular integration. This is generalization of integration by parts. So first, let me recall integration by parts. We have a usual formula. Integral of u dv is u times v minus the integral of v du. This is one format. Or another format is that we have integral of f times g prime, and let's write dx for the variable. Then we have f times g minus the integral of f prime times g dx. Now, if instead of beginning with f g prime like this, we begin with f g double prime, then what do you think we can do? Well, we just apply the previous formula right here with g replaced by g prime, right? If we replace this g right here with g prime, then we will have g double prime. So the formula would becomes like this: f times g prime minus the integral of f prime g prime dx. But now we may use the formula again. So then we have the integral of f prime times g prime here will give us integral of f prime times g minus the integral of f double prime times g dx. Distributing the minus sign, we will have f times g prime minus f prime times g plus the integral of f double prime times g dx. So you see that we could keep going, and instead of beginning with f g double prime, we may begin with the third derivative of g, etc. Then we have a longer formula. But to summarize the process and to make it easier to memorize, we make it into a table. And that's what the name tabular integration. The table, so to do integration, so f g double prime dx like this, we make a table. The first column is had two columns. The first column we denoted by d for derivative, and the second column will be for I, so integrate or integral. We begin with f and then g double prime here. The f comes from the factor of f, and g double prime comes from there. Now for the derivative, we take in derivative, keep taking derivative f prime, f double prime, and for the g we keep integrating. We will have, this is second derivative, we integrate. We have first derivative, we integrate. Another time we have g only, no derivative. And then the formula above reads like this: f times g prime, meaning that we connect this, we multiply f and g prime. And then the next one is f prime g, so we connect that. The last one, we need to do horizontal f double prime g, and the sign, this is a plus sign for us, and then minus, and then plus. So it's alternating. But keep in mind that for the last part, for the last horizontal, we need integral here. Need the integral. It's important. This integral for the for the horizontal product, but for the diagonal product, we don't need any integral. Um, so the this method will help us do integration by parts quicker, especially in the case where we have a problem where the derivative of f eventually becomes 0. Then the last one will be the integral of 0. Then we just have a constant. So here's an example. Let's do the first example. Integral of say x squared x cubed e to the 2x dx. Now we need to split into two pieces. The first one for the derivative and the second for integral. This is for d and this is for the column I. So d here and I there. For d, we keep taking derivative. Now for x cubed, if we take the derivative, eventually we would get 0. That's good. So 3x squared, 6x, 6, and lastly we have 0. Now for integral, we have e to the 2x. We integrate, we have a half e to the 2x. Integrate again, gonna be a quarter e to the 2x. And then 1/8 e to the 2x. And lastly, 1/16 e to the 2x. Now, using the above formula, uh, in the previous discussion, we only had 3 rows, but we could keep going and the pattern continues. So here we connect the diagonal part, do it carefully, and lastly we also have the horizontal, and they say plus, minus, plus, minus, plus, the alternate sign. So the answer is the integral of x cubed e to the 2x dx equal to the first diagonal multiplied together with the plus sign, we have a half x cubed e to the 2x. The second diagonal with the minus, we have 3 over 4 x squared e to the 2x. The next one we have plus 6x times 1/8. So we can simplify as 3/4 x e to the 2x. And then we have minus 6 over 16 e to the 2x, which is 3 over 8 e to the 2x. Lastly, plus the integral. Keep in mind, for the last one, horizontal part, we need to take integral of 0 times 1 over 16 e to the 2x dx. And of course, 0 times anything is 0, so we have an integral of 0, which would give us c. The whole thing here becomes integral of 0 dx, which is c. So the answer is a long one, like this, plus c. So you see that if you do the regular integration by parts, it will be quite long because you need to repeat the integration by parts several times. With the tabular integration, we have a quick answer. Now here's another example we can try. integral of, say, x squared plus x sine of 2x dx. Then we begin with the first column derivative. We'll take polynomial x squared plus x, and then for integration we use sine of 2x. Keep taking the derivative, 2x plus 1, and then 2, and finally 0. For sine of 2x, antiderivative will be minus a half cosine of 2x, antiderivative again, minus a quarter sine of 2x, and antiderivative again, we have 1/8 cosine 2x. Now we have diagonal, 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 and lastly horizontal. Plus, minus, plus, minus. So the answer is, we have the whole thing, x squared plus x times minus a half cosine 2x. Let me write down here. So x squared plus x sine 2x dx will be minus a half. Let me write the constant first. X squared plus x cosine 2x, and then multiply these two together, we get minus, and then minus become plus, so we get plus a quarter 2x plus 1 sine of 2x, and then plus again 2 times this will give us a quarter cosine 2x. And lastly, we need to minus the integral of the product here, but 0 times anything is 0, and we integrate that, we get c. So it's just c here. You could add c or minus c, it doesn't matter because it's just a constant. So this is the answer. Now sometimes after we take the derivative several times, we may not get 0, but we can still solve the problem by using the formula correctly. So here's another example. X squared, say, log x dx. Now for this problem, we need to be careful to choose which part is for d and which part is for I. If we put x squared for column d, then we need to put natural log for the column I, and we need to integrate natural log. That would be difficult to do. So instead, we will put natural log for d and x squared for I. Now taking derivative for the first column, we will have 1 over x. If we take the derivative again, we would have minus 1 over x squared, and even if we keep taking the derivative, we won't get 0. So let's stop somewhere here. Now for antiderivative, this time we will have 1/3 x cubed, and if antiderivative again, we would have 1/12 x to the 4. So let's use the formula now. Diagonal, diagonal, but then horizontal, and we have plus here, minus, and plus. So what does the formula give us? This gives us that the integral of x squared log x dx equal to, multiply these two, we have 1/3 x cubed log x, and then minus, multiply these two together, we'll have 1/12, and then x cubed, because the x and in the denominator and x to the fourth cancel out. Now lastly, we need to add integral of the product here, which is minus times that we would get minus 1/12, and then x squared times in the denominator times x to the 4 will give us x squared dx. But then now we need to integrate. We have 1/3 x cubed log x minus 1/12 x cubed, and then minus 1 over 36 x cubed plus c. We need to simplify the other one, the two terms right here. So 1/3 x cubed log x, and then here we will get what, minus 1/12 minus 1 over 36 will give us, so this would become 3 over 12, sorry, 3 over 36. So we get minus 4 over 36, which is 1 over 9 x cubed plus c. Now for this problem, we can actually stop at the second step right here, and then we use a formula. We don't need to go further like we did. We can stop there and we still get the correct answer.